All right, back to share screen. Okay, so we're focusing on 8.4. This has to do with systems of nonlinear equations in two variables. And so I'm going to show you the diagram and your solutions after we solve. And you'll see why and how you're doing this. So we'll start with straight up example 1. In example 1, they give us a system that starts with x squared is equal to 2y plus 10. And then they tell you that 3x minus 1 is equal to 9. And so they want us to solve for the system, and they also want us to graph the system. Here's what I would suggest to you. Let's use substitution to solve. So we're going to use this as our main equation. And this one, I'm going to restate as, first step I'm going to take is subtract the 3x on both sides. Notice that I'm left with negative y equals negative 3x plus 9. But then I multiply all of this equation by negative 1, and I do that because I want y equals. So now y equals positive 3x minus 9. And what I'm going to do is I'm going to plug that value in here and solve for x. So if you notice, this goes basically in there. So now I have x squared is equal to 2 times 3x minus 9 plus 10. So remember, order of operations, you have to distribute the 2 to the 3x and the negative 9. So now you have x squared is equal to 6x minus 18, and then here's your plus 10. Now at this stage, obviously you can gather those two, combine them, and you're left with x squared is equal to 6x minus 8. Now, you're probably asking what the next step would be. Well, obviously what we want to do is we want to set this to 0. So I'm going to subtract 6x and add 8, subtract 6x, add 8, and you do that on both sides. Now, the reason why is because now this is equal to 0. And now what you have is x squared minus 6x plus 8 equal to 0. So basically a quadratic. And we're going to use that to solve. When we factor this, we know that this is x minus 4. We know that this is x minus 2. And that just goes back to basic knowledge of the trinomials. And so that means that I have x is equal to 4. And I have x is equal to 2. So if I take these two values and I plug them in, I need to figure if this is actually a solution. So I know that when x is equal to 4, this becomes y is equal to 3 times 4 minus 9, and that equals 3. And when x is equal to 2, then I have y is equal to 3 times 2 minus 9, which is equal to negative 3. So I have two solutions, if you notice. And I want you to focus right here. This is 4, 3. And I have another coordinate pair, which is 2, negative 3. Now, the reason why these 2 points are important is if I were to throw these two equations in Desmos, which I'm going to do next, I'm going to show you that these 2 coordinates are actually the 2 points that these diagrams cross across each other. All right, so there are your points. Go ahead and write them down if you need a minute. And I'm going to hop over and throw this into Desmos. If you're ready, here we go. So in Desmos, you're going to see all right, so here's what I have. I have x squared Let me take this off of capital because it doesn't like capital letters. So I have x squared is equal to 2y plus 10. I think it'll actually do it in that format. It does. Okay, so that's done. And then I have 3x minus y equal to 9. And I want you to look here and here. What do you notice? And those are the 2 points that where you can see this crossover happening between the two equations. So you have 4, 3, and you have 2, -3. Those are your two solutions because that is where the values are intersecting. What is also interesting here is that this could also, like I said, be a management decision, and part of your rejection region is obviously where the overlap does not exist. So I want you to think about like a marginal type decision. This would not be a solution area, nor would this, but your solution area would probably sit somewhere in this region right here, where you see this overlap being cuddled between those 2 points. Okay? Questions on that one?
Could you repeat what you just said one more time, please?
That if this were a management decision model, and it happens to mirror two scenarios, you're looking for the solution to be between these 2 points. Anything inside of here would be considered a solution area because that's where you have overlap.
Okay, cool. Thanks.
Potentially. So overall, was that somewhat easier? You want to try another one of those or move on? Your choice. Move on?
Pretty good, yeah, move on.
Move on, okay. All right, in the next example, and again, those are the points you solve, by the way, we saw on the diagram. Okay, example 2. In example 2, we're still doing the same thing. We're using substitution. They're giving us the system where I have x minus y is equal to 3. And then they give us the equation of a circle, x minus 2 squared plus y plus 3 squared equal to 4. And so what we're going to do is we're going to solve one in terms of another. So your choice how you decide to solve for this. I like solving for x, so I'm going to call this equation where x is equal to 3 plus y, or y plus 3 is your choice how you label it. Personally, I like y plus 3. And I'm going to throw that into this part of the equation here. So now this becomes y plus 3 minus 2 squared plus the y plus 3 squared equal to 4. And so obviously these two get combined to give you y plus 1. So you have y plus 1 squared plus y plus 3 squared equal to 4. And now we FOIL. So if I FOIL this, I'm going to have y squared plus 2y plus 1 plus y squared plus 6y plus 9, and this is equal to 4. All right, and so if I'm going too fast, let me know. Notice that I'm going to combine my y squares. They're both positive, so this becomes 2y squared. I have a 2y and a 6y, which combined become positive 8y. And I have a 1 and a 9 to give me a plus 10. And this is equal to 4. Again, I just combined that and that together. If I take out a 2, because 2 goes into 2, 2 goes into 8, 2 goes into 10, I'm left with y squared plus 4y plus 5, and this is equal to 4. Okay, so that's all I've done so far. Am I having a moment? So I'm here with 2y squared plus 8y plus 10 equal to 4. Oh, okay. What you'd want to do, I got ahead of myself. I knew that I caught that off the bat. Before you divide by 2, before we divide by 2, we are going to subtract this 4 on both sides because we need this set to 0. This leaves you 2y squared plus 8y plus 6 equal to 0. Now we can take out the 2. So if I take out the 2, I'm left with y squared plus 4y plus 3 equal to 0. And now I just need to factor this. So I know that this is 2 parentheses. This will be y plus 3 times y plus 1, and this is equal to 0. So my two solutions are here and here for the y's. This tells me that y is equal to -3 or y is equal to -1. But I need you to remember that you have to substitute this back into the original equation that we solved for at the top, which was up here, where x is equal to y plus 3. So I'll bring it here. So x is equal to y plus 3, and we're going to substitute in our values. So I have x is equal to -3 plus 3, which means that x is 0. And I have the other solution, we'll call it x1 and x2. So here's x2, which is basically equal to -1 plus 3, which is equal to 2. All right, and so that means that I have 2 coordinate points. I have this coordinate point where I have 0, -3. And over here, I have another solution, which is where x is 2 when y is -1. So you kind of have to work backwards on this one. So you're using this equation. All right, issues, questions?
So that's the solution. That's it. We just have x1 and x2.
Right, because you have a y1 and a y2.
So the solution is like the coordinate point, right?
Again, yes. If I show you again on Desmos, let me do that. See, like on this one, we ended up with 2 coordinate points, same thing here. So let me go ahead and throw these in here. I have the first equation, which was x minus y is equal to 3.
3.
And this one is,
X minus 2 squared
yeah, x minus 2 squared
plus y plus 3
plus y plus 3
squared equals 4.
squared, and this equals 4. So you have a circle and a line going through the circle. And those are the 2 points we just found. 0 and -3, and the other point 2, -1.
Okay. No, I just wanted to make sure because, I mean, coming to have just 2 coordinate points doesn't give much of an answer. But I think it goes to the management, to the management solution set that you said.
Yeah. Well, that's what eventually, once you get into the inequalities that relate to these types of systems, you can relate it to management decisions. But here, this could also be related to construction or some sort of engineering.
How so?
Well, if that were some sort of beam or some sort of wire, it could be an electrical wire, it could also just be decorative. Those 2 points are the points that you want to intercede based on the design.
Okay.
So, you know, there are multiple applications, not one in particular.
Okay, good to know. We can move on, I think.
Yep. All right. So the next question or example, same thing again. Same thing again. We're still solving a nonlinear system. So this case, we have 4x squared plus y squared equals 13. and I have x squared plus y squared equals 10. So basically two equations again. These could be related to any type of application. So in this case, what you'd want to do, because they are similar, is we could just multiply by -1 in the bottom, which would make this negative x squared minus y squared equal to -10. And as you can see, the y's are kind of cancel. This is going to leave you with 3x squared is equal to 3. And in this case, x squared is equal to plus or minus 1. All right, and so what you'd want to do in this case, remember you have two equations. So if I use the x squared plus y squared equal to 10, and I use both plus and minus 1 in the calculation, because the x is squared, I'm going to end up with y squared equal to plus or minus 9, which means that y is equal to plus or minus 3. Now, that also means that I have 4 answers, because there's 4 combinations of these two responses. I could have, for example, +1, +3, +1, -3. I could have -1, -3. I could have,
Professor.
yes.
But, okay, no, never mind. I see what you mean. Never mind. That's fine.
Yeah, so 1, 3, 1, -3, -1, 3, -1, -3. So you have 4 coordinate point possibilities. Okay, so let's look at those real quick and you'll see why it is what it is. All right, here we go. I'm gonna throw it in decimals again. I'm not sure if I'm going too fast or not. You guys tell me, or maybe I'm going too slow. All right, so let me give you the first equation, in which case we had, let's see, we have 4x squared plus y squared equal to 13. And then on this side, we have x squared plus y squared equal to 10. Do you notice our 4 points? 1, 2, 3, 4. Those are our 4 points of overlap. And so that would be very important if you were looking for parts securing two objects of some sort. Maybe those could be pivot points, points where the objects pivot, for example. All right. Where are we on that? Easy, not easy? One another example, keep going. What am I doing?
I think we can keep on going. It's just finding the points. I don't think complicated.
That's pretty much all of this chapter. All right. All right, going to example 4. There's only one more example and it's an application. I'll do it with you as well. So in example 4, we are looking at y equals x squared plus 3. And again, a circle with its origin point, center point at the origin. So x squared plus y squared equals 9. All right, so you can actually combine this one, and I'm going to show you that method because you're probably not used to it. And so first thing I'm going to do is I'm going to re-express this. This is going to become negative x squared plus y equal to 3. And this one stays the same. And if I were to group these, I would have negative x squared plus y, and this is equal to 3. Over here, I would have x squared plus the 0y, because there's no 0y. Here, this would be 0y squared. Down here, this will be plus 1y squared is equal to 9. And so we're grouping those together. If I group them together, notice that this is going to cancel. And I'm left with y equals, I'm sorry, y plus y squared equals 12. If I subtract the 12 and move it over here to the left side, notice that I end up with y squared plus y minus 12 is equal to 0. And now we factor, obviously the factors are 3 and 4. So this becomes y plus 4 times y minus 3, and this is equal to 0. This is leaving me a solution of y equal to -4 and another solution of y equal to +3. All right, and now what I want to do is throw this into one of these equations. So if I use the equation y equals x squared plus 3, I'm going to substitute in the -4. So that means that in this case, -4 is equal to x squared plus 3, which gives me x squared is equal to -7. So if you notice in this case, that's an imaginary number. So we're going to have plus or minus I square root of 7, not necessarily a solution. But if we substitute into the same equation where y equals x squared plus 3, and I substitute in the +3, then I have 3 is equal to x squared plus 3, which means that 0 is x squared, therefore x is equal to 0. And that could be a potential solution, and that would be the solution 0, 3. When you look at the graph of this, just to save a little time, you basically have a circle. Like I said, its origin at the center, or the center is the origin itself. And the radius is 3 units out. So this circle looks as such. And if you look at, hopefully prettier than that. And if you look at the parabola that they gave you where you have y equals x squared plus 3, this is extending from here out. And so this is the point that we're looking at. That's the common point, which is the point 0, 3, which you just solved for. Okay. Easy? Keep going?
Professor, can you do another one like that?
Yeah, absolutely.
Thank you.
Let's look at this one. Okay, so let's solve for the system where we have y equals x squared plus 5. And this circle is that x squared plus y squared is equal to 25. So let's just draw it first. How about that? Would you be okay with that?
Sure, let's go.
Sure, sure,
Substituting? Without substituting?
sure.
Circle, center 0, 0, radius of 5. Right? Because it's a radius squared, so radius is 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. So very rough draft of your circle. Okay, so let's say this is your circle that going through 5. Right? Now notice that. That's a parabola with a vertical translation up 5 units. So it's going up 5 units. That is a shared point, which is 0, 5. Now, you want to substitute this in? We do the same thing we did last time. So if y is equal to this, then basically we have x squared plus x squared plus 5 squared, and that's equal to 25. All right, so now we do a little math. If you want to do it this way, assuming. If you want to do it the way we just did this question again, you would re-express this as negative x squared plus y is equal to 5. And we will combine it with that equation. So let's do that. You have choices. So we have negative x squared plus y plus 0 y squared. I always like to fill in my spaces. On this side, you have x squared plus 0y plus y squared, and this is equal to 25. So what happens? The x squares go away. Combining the y's, you end up with y plus y squared is equal to 30. And all I have to do is bring the 30 over and rearrange this part of the equation to get y squared plus y minus 30 is equal to 0. So if I factor this one more time, I have y plus 6, right, times y minus 5, and this is equal to 0. So again, one of my solutions is y is equal to 5. The other solution is imaginary, and that's this one, because I'm going to end up with, in this case, y is equal to negative 6. No measurement can be negative 6 in this case. So that's why we have 0, 5 is our equation. If we take the 5, plug it in into either equation, you're still going to get this. So that means that 5 is equal to x squared plus 5. So I'm going to subtract 5 on both sides. So 0 is equal to x squared, so therefore x has to be 0, and it is. So now you see as a diagram, you see it as an algebraic equation. Either way works, right? Are you cool with that or no?
Yeah, it just depends on how you want to look at it.
Mm-hmm.
Yes, thank you.
All right. And example 5. In example 5, I have basically it says you have 36 yards of fencing. To build an enclosure okay, and then they give you a picture which I'm going to share with you in a minute. It says some of this fencing is to be used to build an internal divider. Okay, then it says if you'd like to enclose if you'd like to enclose 54 square yards, what are the dimensions? Of the enclosure. All right. So here's the picture that you're going to need to answer this question. So you've got what looks like a yard or like 2 yards combined together. All of this part is X, and X includes that internal divider. That's what this is. This internal divider right here, and this is Y. Obviously, this is Y also. So when you look at this, I want you to think of a couple of formulas you're gonna need. So first thing you're gonna need is the perimeter formula. So if you think of the perimeter and you think of the fact that this is X, you have 2X plus 2Y plus a third Y. The third Y is the enclosure. And this has to equal 36. So that means that 2X
I'll be there for you.
all right. And if that's the case, then we also know that we have a second condition. That second condition is this is a square yards, basically the area. We do know that area is always length times width. So in our case, X times Y, and that should be 54. So those are our two equations. Equation 1, equation 2. And this is what we know. So at this point, what you'd want to do is solve for Y or X. I'm going to solve for Y equals 54 over X. Give me 1 second. Apparently,
Yeah, Stack is muted.
there you go. All right, so Y equals 54 over X. So now what we want to do is let's use that here. So in that case, that means that we have 2X plus 3 times 54 over X, and this is equal to 36. So now we can solve for this somewhat easily, I would think. So we end up with 2X plus 162 over X equal to 36, sorry, equal to 36. Okay, and what I'd want to do at this point is let's get rid of that X in the denominator. So if I multiply by X on both sides, now I'm left with 2X squared plus 162 equals 36X. I also see that they're all even numbers. So if I divide them all by 2, this gives me X squared. So 2 parentheses X squared minus give me 1 second. I'm having a brain fart. Oh, I forgot to move this over again. Keep jumping ahead of myself. Okay. So we're not going to divide by 2 just yet. We're going to subtract that 36X. So we have 2X squared minus 36X plus 162 equal to 0. So yes, now we were going to divide by 2. I got ahead of myself. You can you're actually, believe it or not, dividing by 2 all the way across even to that 0, but it doesn't really affect it. So you end up with 2 parentheses X squared minus 18X plus 81. And this is obviously equal to 0. And so this is a perfect square. We end up with 2 times X minus 9 times X minus 9, which is basically 2 times X minus 9 squared equal to 0. So that means that X equals 9. So if X equals 9, that means that our Y value is equal to 54 over 9, which is basically 6. And the reason why I said 54 over 9, remember, we did this over here. So that's where that comes from. So our Y is equal to 54 divided by 9, which is 6. That means that dimension-wise, to enclose this, we need 9 yards by 6 yards. All right? How was that one for you? Was that challenging? Okay.
No, it was pretty good.
Good. All right. I want to hop into 9.1. All right, let's go to 9.1. Wait 1 second. Let me locate that real quick in the notes. So So if you notice, it's a lot of substitution, it's a lot of more of the same, and you're just looking for overlap. Where do those points intersect? So we are looking for a solution or a set of solutions, basically. All right, here we go. All right, so we are, by the way, ahead by like almost 2 days, which is good because that relieves the pressure off a little bit and gives you a little bit of catch up time. All right, catch up time is good. All right, so we are now getting into matrices. Let me see how long this section is. And so, yeah, this section only has 5 examples, but they are a little long, I will warn you. And we're going to talk first about what is an augmented matrix, which is very easy. And I think this will come back to you fairly quick. So let me pull the notes up on that. I don't know why my pages are out of order. I'm missing a page, I think. 902, 911. Ah, there it is. Okay. I was getting scared because I couldn't find example 1. Okay, here we go. Everybody ready? Still fresh? Francis Javard? Okay. So this is 9.1. It's all about matrix solutions. This is my favorite lesson to teach. So get ready for the geek to come out. So we're looking at matrix solutions to linear systems. What is really cool about this is that this ties right back to everything you've ever done about solving systems via substitution or addition method or what have you. So we begin with example 1. We have 2y minus z equal to 7. They give us x plus 2y plus z equal to 17. And they give us 2x minus 3y plus 2z equal to -1. So what we're going to write, and this is more so a definition that you're going to sort of adhere to, is an augmented matrix. Anybody going into electrical engineering in this call, you will need to know what an augmented matrix is, because matrices are a severe part of electrical work. Any type of computer system as well. So here we go. This augmented matrix has basically the format of X, Y, Z. And then what happens in the last column is the answers or solutions. So for example, this is 0, this is 2, this is -1, this is 7. The second line is going to be 1, 2, 1, 17. Do you see where these numbers are coming from? On the third line, you have a 2, you have a -3 for the Y, a +2 for the Z, and a -1 for the answer. Easy?
Yeah, it's just looking at the constants, right?
Yeah, just looking at the constants. So I'm going to highlight this row just for the sake of reminding you. That's all you're doing, basically. Easy enough? Okay, in matrices, they discuss what's called a main diagonal. The main diagonal in any matrix usually holds a solution. So this is the 1, 0, 0, and this is the solution for the first answer. 0, 1, 0, this is the solution for the second value. And 0, 0, 1, which is the third solution.
I actually really like these. I remember them from my last class, and they were actually like kind of fun to do.
They are. I like them. So it is important for you to remember this. So that's the main diagonal. I want you to, if you want to extend your knowledge base, Eigen values. Eigen values are huge in finance. Anybody here into finance or interested in a career in investing? There you go. So that that is an Eigen value is used to predict the success rate of a stock, for example. It's one example. There are many uses for Eigen values. We can discuss those at another time. But if you want to look it up, it might be fun for you. I don't know how deep you want to go into this. So there are what we call matrix operations. You know how in math we always have the order of operations? Here we have matrix operations. So matrix row operations, there's 3. The first one is you can exchange a row for another. They call them I and J, by the way. So when you think of these rows, they are known as I and J values. Columns and rows, basically. So you can swap row I and row J. So as an example, which we're going to do next, I'm going to give you this matrix where I have the following values in row 1. Row 1, I have 3, 18, -12, 21. I have 1, 2, -3, 5. I have -2, -3, 4, -6. So if I call this row 1, row 2, row 3, as an example, I can swap, which is what this means, swap row 1 with, let's go extreme, let's go with row 3 as an example. So if I'm swapping row 1 and row 3, then my next matrix will be -2, -3, 4, -6. The 1, 2, -3, 5 stays. And this is 3, 18, -12, and 21. So I swapped literally rows 1 and 3. Easy to understand? Yes?
Okay, but yeah, but what would be the point of just swapping the answers? Would that
Oh, Wasabi, you shall see. You shall see. So that is one row operation you can do. This is when we're solving using either row echelon or the Gaussian elimination, depends on which one we're going to use. So the next example, we'll go back to the original matrix. I'm going to ask you to solve for 1/3 of row 1. So basically, I'm going to take all of row 1 and divide each of these by 3, or multiply by 1/3, which is the same thing. Right? This is going to give you a new set of values. You're going to end up with 1, 6, -4, 7, 1, 2, -3, 5, and no change to this, the second and third rows. So this stays the same. Super. Is that easy enough to understand what I just did?
Yeah, you give me a second so I can copy it down, please.
Yeah, no worries. Let me know. I get excited. I start talking fast. Now you need to know these matrix row operations because we're going to use this to solve for a solution without a calculator. Granted, the calculator can solve this for you, but I'm not going to show you that because then that would be cheating. Not really. I'm not allowed to. I have to show you how to do this from the ground up. Can I move on or are you still copying?
I just finished, yeah, sorry.
No worries, no worries. Okay, the third row operation, the last one that you can do, is you can always multiply a row. So just as an example, I'm going to multiply 2 times row 2, and I'm going to re-express row 3 using those values. If you notice, I finished at row 3. And so row 3 is now going to be renamed as the function of 2 times row 2 plus row 3. All right, so I'm going to now go back to my original. Let's go back to the original. So again, we know that our row 1 is not going to change. This is 3, 18, negative 12, 21, no change. Row 2, no change. 1, 2, negative 3, and 5. And here's my row 3. Since I finished with row 3, that is the row that's getting a change. So row 3, so 2 times row 2, so 2 times 1 plus row 3, which is a negative 2. So I have negative 2 plus 2, which equals 0. So my new value for row 3 in the front is 0. So 2 times row 2, 2 times row 2, so 2 times 2, 4, 4 and negative 3, because remember, this is the value. So you end up with, in this case, negative 3 plus 4, and this is equal to 1. And then we repeat the process again. This is now going to be 4 plus what ends up being negative 6, because we're going to multiply 2 times negative 3, which is negative 6, and negative 6 plus what was already there, which is a 4. And all of this gives us our new value, which is negative 2. And we repeat the process even in the answer column. In the answer column, I'm going to end up with 2 times 5, which is 10, and 10 minus 6, which leaves me 4. And so that is my new set of values. So I have 0, I have 1, I have negative 2, and I have positive 4. And those are my new values for row 3. Okay, so that is that example. Do you want to try one of these and do all 3?
Yeah.
Or yes? Okay.
Yeah,
Just
could
one
you?
second. I'm trying to simulate everything.
Yeah, that last one was a little weird. Could you
Okay.
could you explain that one more time? So you get
Yeah.
you multiply the value of row 2 by 2, and then you add it to the value of row 3?
Yes.
Yeah, just
And
bring the
row 3,
diamond down a little.
and row 3 is the one that changes. Whatever you list as your last,
Right.
that is going to be the row that gets affected. So I could say negative 2 times row 1 plus row 3 in this case, for example, as an example. So whatever I list last, that's the one that gets changed. All right, so let me have you try this one. I'm going to be quiet for a minute so you can. This is your original. All right, and so I'm going to ask you in A, I want to swap row 1 with row 2. What is that going to look like? In B, I want you to take 1/4 times row 1. And in C, I want you to do 3 times row 2 plus, and it happens to be a row 3 again, but it could be any row. Could be row 1 as well. All right, go ahead. I'll give you a few minutes. And tell me when you're ready for me. I assume part A is super easy, yes?
Yeah, I actually think I'm done.
Me
Okay,
too.
so
Let's see.
part A, you're basically swapping these two. So you're gonna have 1, 6, -3, 7. You're gonna have the 4, 12, -28, and then you're followed by the -3, -2, 1, -9. So that's a no-brainer, right?
Right.
That's easy, I assume. Then 1/4 of the first row. Basically, all of these get divided by 4. Right? And so this should become 1, 3, -5, and 2. And nothing happens to 1, 6, -3, 7. Nothing happens to -3, 1, -2, 1, -9. Easy enough?
Yeah.
Anybody want to cry yet? No? Okay. Okay, going back to the original. Back to the original. So we're going to go back to our 4, 12, -28, 1, 6, -3, 7, and -3, -2, 1, -9. All right. So according to this, what's going to get changed is row 3. So this says 3 times row 2 plus row 3. The reason why they use row 3 is because you can actually write down the math right below it. It's easy to see. So that means that this is 3 times 1 plus -3. So this should result in 0, right?
Yeah.
Okay. Over here, this is going to be 3 times 6 plus -2. Over here, this is going to be 3 times, 3 times -3 plus 1. And lastly, this is going to become 3 times 7 minus 9. And so the solutions, I didn't do the math in my head, so let me go here. So this is 0. This is going to be 18 minus 2, which is 16. This is -9 plus 1, so this is -8, and this is 21 minus 9, which is 12. And so all of this row goes away, and these are your new answers right here. All right?
Got it. Yay.
Super. Okay. So you were asking, why am I teaching you those 3 things? Here we go. Example 3. Now this is where the fun begins. If you like Sudoku and those types of puzzles, this is kind of like the same thing. So you're going to use Gaussian elimination. So let me explain to you what Gaussian elimination is with back substitution. So we have this with back substitution. Okay, so here's what you have. You have 3x plus y plus 2z equals 31. We have x plus y plus 2z equals 19. And we have x plus 3y plus 2z equals 25. Okay, so as I walk you through the first one, is step 1 is, let's write it in an augmented matrix. Augmented matrix. So we're going to begin by writing this out as 3, 1, 2, 31, 1, 1, 2, 19, 1, 3, 2, 25. So that's like, in a sense, your step 1. Now, at this point, this is where you start to strategize. And I always suggest that in step 2, we're going to focus on the 3 and making that a 1. So you see how you have 3, 1, 2, 31. This is 1, 1, 2, 19. And this is 1, 3, 2, 25. So we want this to be a 1. So this is like our step 1. You could simply swap. This is where swapping comes in handy. If I were you, I would swap rows 1 and 2. So in a sense, think of it as this is going to become row 1 swaps with row 2. So now just by swapping alone, you've got 1, 1, 2, 19. You've got 3, 1, 2, 31. And you've got 1, 3, 2, 25. Okay, so we have what we want. Now, you do notice that ironically, yes, you have a 1 here, but don't get focused on that because technically my next point of focus is here and here. I want zeros. Remember the original matrix I wrote for you, and I said you have 1, 0, 0, 0, 1, 0, and you have 0, 0, 1. You're kind of going for that. So you start here, you go here and here next. That's kind of the pattern you follow. I promise you that is the one thing that will be consistent. So if I focus on making that a 3, I'm going to simply say then, okay, then -3 times row 1 plus row 2 would work. I could also do -1 times row 1 plus row 3. That would make that a 0. Here's what happens. This becomes, again, you have 1, 1, 2, 19. The top does not change, but this row is now -3 times 1 plus 3. This is -3 times 1 plus 1. -3 times 2 plus 2. -3 times 19 plus 31. This second row, or the third row, becomes -1 times 1 plus 1. This is -1 times 1 plus 3. And this is -1 times 2 plus 2. And this is -1 times 19 plus 25. So as you can see in doing the math, your new matrix that has now been created from this is going to yield you 1, 1, 2, 19, nothing changed there. This becomes 0, -2, -4, -26. And this is 0, 2, 0, and 6. That's your new matrix for that. Now, to do Gaussian elimination, my next point of interest is here. That has to be a 1. The easiest way I can make that a 1 and not really affect anything else is to do -1/2 times row 2. And that's going to change my row 2. My row 2 is now going to become, and I'm doing this in stages so you see the big picture. This is 1, 1, 2, 19. This is 0, 1, +2, +13. And here you have 0, 206, nothing changed. The only thing that changed at this point was this row from this calculation. The next point that should be of interest to you is going to be right here. We want that to be a 0. So to change this, I'm going to simply say -2 times row 2 plus row 3. And this is going to take you a little bit of practice. I have students that whine and complain that there's no easy way to do this. It's difficult. It isn't. It's like driving directions. If I say to you, hey, I need you to go to West Palm Beach, there's a general direction. You're going to generally go north, assuming you're south of that. Ideally, right? But there are many ways you can get to the same direction. So this is going to become -2 times 0 plus 0. Okay, this one is going to become -2 times 1 plus 2. This one is now -2 times 2 plus 0. And this one is going to become -2 times 13 plus 6. Our final answer for this matrix is now 1, 1, 2, 19, nothing changed. 0, 1, 2, 13, nothing changed. 0, 0, -4, -20. So what is necessary now is to make this, make sure that that 4, -4 is now a 1. So what I'm going to do is I'm going to multiply by -1/4 times row 3. This is 0, this is 0, this is now 1, and this is now 5. And so now I can look at this as XYZ, where Z is equal to 5. Here's where the back substitution comes in. I figured that this is Z. Z is going to be, in this case, a 5, because this became a 5, right? Because my new matrix is, again, 1, 1, 2, 19. I have 0, 1, 2, 13. I have 0, 0, -0, 0, 1, because we solved for this, 0, 0, 1, and +5. Because these are both zeros, that's why I say that Z is 5 and there's no question. Here in this equation, what I have is basically 1y plus 2z equals 13. And if I substitute in 5, obviously 2 times 5 is 10. Subtract the 10, you're left with 3. So now I know that y is equal to 3. The other thing I know is the equation for the top, which is x plus y plus 2z equals 19. But guess what? I know y and I know z. So I know that x plus 3 plus 2 times 5 is equal to 19. I know that this is 10. 10 and 3 is 13. So x has to be equal to 6. So my solution set for this matrix is now 6, 3, 5. In essence, x, y, z.
So I'm kind of lost. Because
Where?
okay, you said C is equal 5.
Z is equal to 5, and you know that because you've reached this point where it's 0, 0, 1, and then 5. So we know for a fact that Z is 5.
Oh, okay, yeah, because X is 0,
Equation,
Y is 0,
right.
and Z is 1. Is 1 by Z, and is equal 5.
Right.
So therefore, 1 by
And the other 2 are
5,
zeroed out, yeah.
Got it. Okay.
Yeah,
Now-
that last part really cleared it up.
In this equation, you see how I have 1y, because remember, this is x, this is y, this is z, and these are the coefficients. So this is 1y, which is why I wrote 1y 2z, and that's equal to 13. And you already know that z is 5, so you have 10. So you already know that this is 10. If I take away 10, I'm left with the solution for y. So now I have y and I have z. Wonderful. Here's x, here's y, here's z. Here's the answer. Plug them in again and solve. And that's how I ended up with 635.
This is like a game.
It is. And I want you to try one more. Try one for for the sake of practicing this. So let me give you,
And it's always that pattern that you want to get it to the 0, 0, 1
if you,
at the
yes,
bottom.
if you follow my advice and you start with, sorry, the natives have gone wild. Hold on. All right. I'm right here. So if you follow the pattern where you start with the position, let me just
With the first row, right?
yeah, always start here, number 1. Make that a 1. Then make these a 0. After you're done with that, then you go over here. Make that a 1. Then make that a 0. Then make that a 1. So literally in that order. See how
Hold
in
on.
this one I did not tell you that I had a value yet, and I didn't. Because that's not complete. It has to be 0, 1, 0 or 0, 0, 1, that kind of thing.
Could you go up and say that order one more time?
Okay, so you're gonna go, I'm gonna number them. So this is number 1, this is 2, this is 3, this is 4, this is 5, and this is 6. I would do them in that order. So by the time you have like 1, 0, 0, 0, 1, 0, 0, 0, 1, then you should at least have one value, and you should have at least an equation you can use.
Okay, I took a picture of it because like I got lost writing the notes, like
Okay.
keeping up, so it's okay. You can just move on.
No, let's
Thank you.
do another one. All right, let's do another one. I want you to practice this one. So go ahead and try. I'll give you about 5 to 10 minutes. We could take the rest of the period doing these. I have examples 4. Hang on, example 4, and example 5. So just a few more examples. So we're doing good. All right, so here we go. Okay, so we have 2x plus y plus 2z equals 18. We have x minus y plus 2z equals 9. And I did record this, by the way, so you can always go back and watch the recording. You have x plus 2y minus z equal to 6. You actually already have the recording because I uploaded this a while back. All right, so go ahead, try. Let's see how you do. I'll give you, how long do you think you need? 5 minutes, 10 minutes? Let's give you 10.
I mean, I know for sure I'm gonna get stuck somewhere.
I'm gonna give you 5. At 5, I'm gonna check, and then I'll give you 10
Yeah.
if you're moving on.
Thanks.
All right, go. I set a timer. Didn't pay attention to it because I still don't know what time I set it to, but how are you doing?
I'm getting along, but slowly, but moving forward.
Are you moving forward? Okay.
Yeah, it's just
5
like
more minutes?
sure.
5 more minutes. Let's see how far you get.
Professor.
Go ahead.
So I just noticed something in the previous example.
Yes.
The pattern that we're actually trying to look for is to have one on each row.
1 0 0, and then make this a 1. So this should be a 1, this should be a 1, this should be a 1. And these 3 down here, this should be a 0, that should be a 0, that should be a 0.
And the top ones don't matter?
Not yet. Not
Okay.
yet, because right now we're doing Gaussian elimination with back substitution. The next one, the next step is to eliminate these guys and make these zeros. And that will give us our full solution.
Okay, so for now, all we have to worry is to get one across and then the last 3 on zeros.
Right, because of the way we're doing it, this is called Gaussian elimination with back substitution. In other words, you're going to get a solution, which usually it's Z, and then we usually go back and we substitute it in here, and then we finish here. And then you have X, Y, and Z. Now, this next step, which I'm actually going to do next before we get to the four variable one. Don't cry.
No, I was about to break my head on how to get zeros up there. And then I realized that you didn't get zeros there.
Not yet, but we are going to. The next, so this is called, just to refocus you, this is called Gaussian elimination with back substitution, which is why we substitute back. That's why we call it back substitution. Right? Okay, now we continue forward and we make these zeros as well. Now we're doing Gauze Jordan. This is called Gauze Jordan, which we're going to do next. I'm actually going to use this example to keep moving forward. All right, so I'll give you a few more minutes to give you a chance to get the answers. By chance, is there anybody who thinks they have the answers? Or no, not yet. All right, keep working. I'll give you a few more minutes and then we'll talk.
Does Z equal 3?
Yes.
You're lying. Does it really?
Yes, it does.
No way, I figured it out.
Okay, did you get y is 2?
Well, no, I wanted to make sure I got that right before I kept going, to
Okay,
be
keep
honest.
going. Keep going. I'll give you a few more minutes.
Professor, just to make sure, which equation do you like plug in like the values like into? Like,
I would start with the take the z, plug it into the second one, the middle one.
but like the original matrix that you build up, or like the last one that you like
The
got
last
to
one you end up with.
the last one, right?
Yeah.
Okay.
So the way I would approach this particular question, who has the matrix broken down all the way down to where z is 3?
I do, but I did it like so unorganized. But I have it.
You should have this if z is 3.
I have that, yeah, like all the way at the
Okay,
bottom in the corner.
what's your first line?
Like how I first got started.
At this point, when your matrix looks like this, what's your
Oh,
first and second
it's
line?
0, 1, 2/3, and then 0. Oh no, that's just, I'm sorry, I meant that as a second line, like the middle one. That's the one you were asking about.
Okay, so this is the second line is 0, 1, 2/3,
0,
and 0. Okay, and the
Yeah.
first top.
1, -1, 2, and 9.
Okay, so at this point, this is what you have. You have z equals 3. If z equals 3, notice that you have y plus 2/3 times z equals 0. We know z is 3. That's going to cancel. So now you're left with y plus 2 equals 0. So
So
now
what's
you
-2?
know, well, y should equal positive 2. Y should equal positive 2. So there's something off.
It should be a negative 2/3.
Then that makes it, that would make it y is 2. Because this would then be y is negative, or this would be then y minus 2. That makes sense. So now you have two of the values. You have z equals 3, you have y equals 2, and now you've got this x minus y plus 2z equals 9. Somebody verify if this is good. So we should have x
Yes.
minus 2 plus 2 times 3 is equal to 9. This is going to give us x plus 4 equals 9, and therefore x is equal to 5. And now we completed the solution.
I
Here's-
wonder where I made that mistake.
That's probably simple math. All it takes is one wrong turn, and you're back to square one.
Yeah, I just realized because I did make a mistake on my. Now I'm actually just on the second line, the same thing he has.
You have to go back. You have
I
to go
just
back,
got there.
and that's okay. This is gonna be one of those chapters. You're gonna love it, and then you're gonna be totally frustrated by it. Okay.
Professor, there are so many places to make errors.
Oh yeah.
Is there?
Oh yeah.
Oh my goodness.
This is but again, you guys know I've been teaching this since the Earth became formed. So long story short, I hear it all the time. I hear the frustration, and students want the, it's like, isn't 2 + 2 4? Come on, and it's like, it's not that easy. You just have to go back, see where you made a mistake. Let's fix it, revisit it. That's all. All right. I want to show you Gaussian or Gauss-Jordan elimination, which all you've got to do in Gauss-Jordan is, you see how you stop here at this point? You see how you're here? You keep going, basically. So Gauss-Jordan, all it is now we're going to solve for this to be 0. So that has to be zeroed out. We then need this to be 0. We zero that out. And then we need this to be 0, and we zero that out. What ends up happening, to make this long story short, is you're going to end up with 1, 0, 0. And I want you to focus over here. This will be 5. This will be 0, 1, 0. And this will be 2. And this is 0, 0, 1. And this is your 3. Notice that those are the answers. This is not back substitution. This is the Gauss-Jordan. And you are basically solving the entire matrix, in essence. That's what you're doing. Cool? Are we good?
But can't you just solve solve the equation like you just did, get those 3 values and then just write it like that?
Right, but they're going to ask you to solve this using Gauss-Jordan, and then they're going to ask you with the
Like the equations in the mid step, for those zeros, right?
They're going to ask you it all, so.
So we have a way to get the answers. It's just not complicated enough.
Basically. In other words.
Well, since you're going to go there, I have to now show you how to do a 4-variable matrix.
You put that very well. I agree.
Since Steve went there. All right. So I'm not going to do that to you. I'm not that mean. We're going to stop here. It's the same process for 4 variables, 5 variables. Actually, and I'm not bragging, but I actually got curious. I was in one of my classes, and it was one of those master's level math classes, and I said to the professor, how many variables can this go out to? And he said, infinite. And I said, let's do 20. So I created my own Eigen value table. Got me the A in the class.
Professor,
That would drive me nuts. That would be oh my God.
Teacher's a nerd. No, you can lock me up in the room, turn the lights off, forget about me. You can come dust my dead body off. I'll be happy as a pig playing with the numbers. Give me the numbers all day long. Yes.
Professor, what's that thing called where you cross off a row and a column, and then you take the 4 digits on the corner or whatever?
The determinant.
Yeah, that I hate that. That sucks.
That's next. That's next. You're gonna love it. And you know the TI-8384 calculator actually does all of this for you.
I can see the happiness in your face right now because I know you love the topic.
Love this crap. I don't know what it is about matrices. I like linear systems and matrices. I love working with that imaginary numbers and all that. Spatial math. Love it. Love it. Love it. I missed my calling, and here's something you don't know about me. I found that I was adopted, first of all. Let's start with there. But I was raised in a Hispanic community. Hispanic communities do not like girls in math. Guess what subject I was pushed away from?
Math.
And that was the one subject that I could close my eyes, go to sleep in class, I'd be done with the work in 5 minutes. Go figure. So anywho, but had I been pushed into doing math, then I probably would not have been, I don't know, working somewhere else.
Or have you always been this good at math?
Yeah. Yeah, that was my saving grace in school. Yeah. Not a language arts person. Don't tell me to read a book. Don't tell me about history because I think it's a bunch of lies and a lot of omitted information. I'm not saying it's all lies, but I don't know.
Numbers don't lie, that's for sure.
Thank you. See, you understand my mind. I
understand what you're saying. The thing is, like, the books are written by who wins the battle.
Who's the author? We can discuss that another time. So anyway,
we're gonna have time.
Yeah. All right. So, do you guys overall in the class, is there anybody crying on me, or are you good? You feel confident? Are you good for this?
I mean, it's just really, really, really difficult, to be honest with you, just because, like, I mean, I've never seen something like this before, and I've never approached math like this. It's always been, like you said, 2 + 2 = 4, and this is not 2 + 2 = 4. This is, like a million ways that 2 + 2 can equal 4.
I want to show you something. Come here. Nikolai, I'm going to focus on your screen for a minute. Look at the architecture. How beautiful. He's in Russia.
Really?
Look at
He
that.
did that himself?
Look at, no, I don't know. I don't
okay.
know.
But that's beautiful.
But that is the architecture. Isn't that
is
amazing?
Gorgeous. That looks like the
I know, right?
pine
Yeah.
ceilings that are down in the Keys when I redid the house down
Right.
next to Irma.
Yeah.
There was this closet that the whole ceiling was Dade pine like that, tongue and
That's
groove.
gorgeous.
And somebody had painted the rest of the house except in the master bedroom closet.
Awesome.
So I left it.
You like it?
Love it. Love it. The architecture is
Thank
amazing.
you.
That is like
Yeah.
the math and skill and architecture behind that is bragworthy. All
Professor, I
right.
think you're the first person I've ever met that looks like at architecture and says the math behind that is amazing. I've never heard of that before.
Do you know how much math there is in architecture?
Of course, but like I've just never heard somebody be like so like drawn by that. But it's cool.
It's all the measurements, all the detail, look
Right.
at all those angles. And
every
you're
time that you
understanding
make
that
something,
has got to
it's
keep
lost.
the elements out. So what's keeping it out for the majority? Because one wrong angle, one wrong cusp turn, you've got a problem. So
Yeah, it's so complex. Pretty cool.
It's pretty awesome. Okay. Is
Thank
there
you, guys.
anybody in the
Thank
class that wants to cry, or are we good? You gonna be okay? Let's practice. Go to Pearson. I'm here to help you. So just tell me what's up. Go to Pearson. If you want to start with 8-4, that's fine.
I'm just gonna keep on the calculation we already had until I finally get the answer by myself. I copied the answers anyway, but I just want to get to there by myself.
Good. Cool. Very good.
Okay, I'll send you one more frustration. I'll be back.
Okay, I'm here if you need me.